Hello everyone, and thank you for coming to our virtual presentation of Euler, detecting network lateral movement via scalable temporal graph link prediction. I'm Isaiah King, and I co-wrote this with Dr. H. Howie Huang, and both of us are from the George Washington University School of Engineering and Applied Sciences. So, when we use machine learning for anomaly detection, the way that we abstract the data defines what we call an anomaly. And there's two popular ways of representing network data. There's the events-based way and the frequency-based way. The events-based way looks at each event, like two machines talking to each other, in isolation, and it defines an anomaly as an event that has strange features or unusual information about it, like the number of bytes or what protocol it uses and so forth. The frequency-based way of representing a network is instead looking at the temporal information surrounding events. So how quickly events are coming in, or what the order of different events is. In the frequency-based way of looking at things, the way we define an anomaly is if they come in at an unusual speed or an unusual order. And both of these are good for certain things, but the way we see it, they neglect to take into account the more structural view of a network. And to this end, it's becoming more popular to represent networks as graphs. A graph is very good because you're getting this information about which entities are connecting to which other entities. You can create structural relationships. And it's especially better suited for lateral movement detection, where we can look at edges and identify which edges in the graph are anomalous. The problem with this is that it doesn't take into account time. So we propose this solution of using temporal graphs. Now we use discrete temporal graphs, which means we look at all the activity in a network over a given period of time, construct a graph out of that activity, and then move to another time window and construct a different graph. When we're using temporal graphs, we can use temporal link prediction. And there's a couple of different ways of doing this, but they all boil down to the same thing. We're trying to find a function of two nodes and a timestamp that outputs the probability that an edge exists in the graph, in the temporal graph, at that time or at some future time, given what we know about the past graphs. If we're trying to determine the probability that an edge exists given some partial snapshot of the graph and all the previous graphs, we're calling that dynamic link detection. We're looking at if there's going to be an edge right now. If we're trying to decide if there's going to be an edge in the future, given what we know about the past graphs, we call that dynamic link prediction. So here's a motivating example. Suppose you have this little toy network with Alice and Bob. Alice talks to computer 0, Bob talks to computer 1, and after they've both talked to their computers go and get some information from the shared drive. You'll notice in time steps 2 and 3, when only Alice talks to her computer is the only one that goes and gets information from the shared drive. So now let's look at time steps 4 and 5. Alice authenticates with her computer, Bob doesn't, but both computers still go get information from the shared drive. How do we detect this using the previous methods? Well, if we're using the events-based method of abstracting networks, it would be very difficult to see this as anomalous if all the features of that connection were normal. If the computer was just off on its own making a normal connection without having been authenticated first, it might look exactly the same as if Bob had authenticated first. It's very hard to see. Similarly, with frequency-based events, the events of Bob a time step earlier have very little to do with a connection between computer 1 and the shared drive. The topological structure of the graph is not being taken into account. But even using graph-based methods still won't detect this anomaly, because if we're using the traditional way of representing a network as a graph, all of the edges, regardless of when they occur, are going to be encoded the same way. So the anomaly score of the edge at time 1 from computer 1 to the shared drive is going to be scored exactly the same as it is in time step 5. So the only way to really capture anomalies like these are with temporal link prediction using a temporal graph. So temporal link prediction is most often done in the method in the top right box, where you take a graph, you pass it through a graph neural network. The output of the graph neural network goes into a recurrent neural network, which outputs a node embedding, as well as the input for the next graph neural network. This forces the whole process of embedding temporal graphs to be sequential. which is not really feasible when we're looking at network logs, which can span days and days. So we propose uncoupling the GNN and the RNN so that all of the GNNs can operate in parallel, while all of the recurrent neural networks operate when the GNNs complete running. Because the graph neural network is the most complex part of this approach, and the graphs are the largest data structure that are getting compressed into smaller embeddings, we're exploiting Amdahl's law here and allowing the big part of the work to be done in a distributed fashion and the easier part of the work to be done sequentially. So here's how we do it. This is the Euler framework, and I'm going to go step by step through each stage of it and explain what's happening. In the first step, we're just loading the data. The worker machine, which holds the recurrent neural network, spins up several worker instances which all hold their own graph neural networks. Those worker machines then go collect contiguous graph snapshots and report to the leader when they have finished loading everything in. Once everyone's finished loading in their data, the leader issues a command to all of the workers to use their graph neural networks to make a topological embedding of the graphs. Because all the data is stored on the workers, there's very little network traffic. Finally, once all the graphs have been condensed into the smaller embedding form, those embeddings are passed back to the leader. Now, the leader computer can start operating on those embeddings as soon as they come in, because they have to be processed sequentially. So we imbalance the data a little bit so that workers holding later portions of the graph have more data and workers holding earlier portions of the graph have less. This way, the recurrent neural network can also operate in parallel with some of the worker machines if the data is balanced right. When the leader finishes encoding all of the topological embeddings and how they change over time, it's going to output its final topological and temporal encoding, those Z matrices you see up there. Finally, we either score or calculate loss, depending on if we're training or evaluating. If we're scoring, the leader will determine which embeddings need to go to which worker for them to properly do link prediction or link detection. And the workers all, in parallel again, calculate loss based on those node embeddings and they measure the probability that the edges that are in their graphs should be there, as well as the probability that edges that are not in their graphs, just randomly sampled negative edges, should not be there. Finally, the workers all return their loss back to the leader, which combines them. Backpropagation occurs. If we're evaluating, the leader will then calculate AUC or AP and so forth. Now, the loss function is pretty simple. The workers will sample some number of random negative edges that's equal to the number of positive edges that they have at the time step they're evaluating. And in addition to that, they'll calculate loss on all their positive edges. The way this is done is you take the embedding for one node and the other node, and you calculate the inner product. If the inner product is close to 1, then there should be an edge between them. If the inner product is close to 0, there should not be. So because of this, we use binary cross entropy on the positive and negative edges to calculate loss. So before we test this on a cybersecurity dataset, we wanted to make sure it worked well as a temporal link predictor in general. And to this end, we compared it to several state-of-the-art methods. We compared it to semi-implicit VGRNN, which is currently the #1 ranked temporal link prediction model on Papers with Code. We tested it against evolving GCN, which uses a similar system of current neural networks and graph convolutional networks. And we also tested it against DynGraph TVEC, which does not use any graph neural network components. Everything is linear layers. It does use a recurrent neural network, however. And the results were pretty good. They showed that Euler constantly outperformed or performed as well as the state-of-the-art. Ties here are based on the p-value of a student t-test. So we only report that Euler or another method performed better if it performed well enough that the p-score was less than 0.05. And what we learned from this is that using a recurrent neural network and a graph neural network in conjunction is very useful for temporal link prediction. This provides a lot of data about the changing dynamics of the graphs. However, it's not so important to have that RNN output be put back into the graph neural networks that can all operate independently, and it does not have to be in serial anymore. So now that we have that knowledge, we can finally test it on a real-world cybersecurity dataset. We chose the Lateral dataset, which has 58 days of log files in a real-world system that undergoes an attack campaign. The red log identifies 750 authorization events evolved in compromise out of about 46 million total events. So it's very imbalanced, as it would be in real life. And we build a graph, a temporal graph, by looking at all of the authorizations that take place during a 30-minute period and construct nodes which have features based on if they're a computer, a user, or a critical system component like the domain controller, as well as a unique identifier for each node. We also use weighted edges based on how many connections any two nodes had. And for classification, after training, we calculated at which threshold the true positive rate and false positive rate were both optimal, with slight biasing for the false positive rate to be low. We found that using a lambda value of 0.6 here was optimal. And here are the results. As you can see, our method Euler outperformed all other methods in all of the classification quality evaluations, such as area under the curve and average precision, which means that depending on where the threshold is, our methods will perform better than the others tested. Additionally, in the classification tasks, you can see that Euler had quite good false positive rates, not better than VGRNN in the link prediction tasks, but still quite good. And you can see because the area under the curve for Euler is much higher than VGRNN's, perhaps if we adjusted the threshold, then the false positive rate would be as low as VGRNN's without affecting the true positive rate quite as much. So in terms of performance, as stated before, this does speed up the process of link prediction quite a bit compared to the other methods. In terms of forward propagation time through the network to make a decision about the likelihood that two nodes should have an edge, Euler was about twice as fast as the best method we compared it to. In terms of backwards time, how fast we can train it, Euler was 16 times faster than the second fastest method we tried. And what this shows is that as you add more workers, the performance seems to just continue improving, as long as up to a point, obviously. But because Euler used 16 workers, we tried to have a fair comparison by letting all the other methods use 16 interoperation threads. But as you can see, letting the graph neural network portion of this be distributed was just such a benefit compared to being forced to do that part in serial, to the point where it didn't really matter how many interop threads we gave the other methods. So in conclusion, Euler accomplished the following. It was consistently as powerful or better than prior works in the benchmarking tests. We parallelized temporal link prediction. To our knowledge, this is the first use of graph temporal link prediction for an intrusion detection system. And of all the methods we tested on the Lateral dataset, Euler achieved the best scores. In the future, we'd like to see if there's uses other than anomaly detection for Euler's embeddings. Perhaps we can use them for clustering to describe various components of a network. We'd like to test other decoding functions rather than simple inner product decoding, because there's a lot more we could probably get out of those embeddings. And finally, just using distributed graph neural networks in general. There's other places where this can be useful beyond just cybersecurity. So if anyone has any questions, I will be answering them live, I think. And yeah, thank you for coming to our presentation.